All right. So that begins another important aspect of microbiology, uh, viruses, virology. We have 10 lectures on that. And I think the design of the course is, I believe, one or two, or maybe one lecture is a take-home lecture, and we'll go through that in the end. But today's lecture will talk about the viral classification, structure, and replication. And as you can see from this figure over here, viruses look like particles. There was a time that we did not even consider, or we were struggling to figure out whether they are really outer space stuff or what were they, or they were just like crystals and so on and so forth. But now we know for sure that there is something else going on with these viruses. Now, when we talk of viruses, and again, those of you who use computers, email getting viral emails, we talk about virus getting into a computer, and we talk of antiviruses programs and so on and so forth. So it doesn't really mean an actual virus, but it means the spread. It means infectivity. It means something out of control. It's something of that nature. So that word itself stands for a good purpose for us to know how are we going to deal with viruses. Okay? Now, today, in this lecture, I'm going to go about the properties of viruses. And also keep in mind that this is a journal lecture, and very important lectures. Once you understand that, it will help you understand viral diseases. It will help you understand antiviral therapy. So these are foundational. And we'll also describe what actually virus is and how do they replicate. And I already gave you an example for the computer when they talk a video getting viral, email getting viral, totally out of control, out of proportion, and ability to replicate so fast. So that's the challenge that we have in terms of viruses. Now, keep in mind, different people have had different definitions for that, but I like this definition. It just kind of conveys you a message there, which says, a piece of bad news wrapped up in a protein coat. So it is bad news. So viruses, because when you talk about bacteria, I may have mentioned good bacteria, bad bacteria, pathogens, so on and so forth. By all means, depending on how bad the news is, it is considered as a bad news. Now, some of the general properties of viruses, they are filterable agents because they have very small size. And remember, we talked of seeds, we talked of mycoplasma, and we talked about the size 0.5 micrometer, if you remember. So we cannot use that sieves or purification methods when we talk of viruses. And also keep in mind, we talk of sterility. The challenge is how to make a injection, how to make a liquid or any other sort virus-free. So there is definitely a challenge on our part. Now also keep in mind that they are intracellular and they are not parasites per se, but parasite in literal terms, that they are dependent on others for survival. You can see they are dependent on survival. They cannot live or, well, they can live, but they cannot duplicate or replicate on their own. They are dependent on the host cell. You want to pass the tendencies on? Yeah, pass it on. Yeah. Now, they cannot make energy or proteins independently of the host cell. When I tell you that, so what I'm trying to, because each and every property has a bearing, you know. If you get infected with bacteria, you get bacterial viruses, but you can see viruses can debilitate you because The viruses are using your energy, your proteins for their own survival. So you will feel weak. Does that make sense? So they are going to depend upon your energy level to take it away from you and cause problems. The other important thing, since they are dividing, so they have to have a genome, and by far, and I'll still stick to it, even in this class, I said last year as well, that they can either have an RNA or DNA, but not both. But that is not true. Now, I think maybe the new book has changed, but right now I would still want, because many of you may not have taken virology before, I don't want to confuse you, but the fact is that the last statement has changed. They can have both, right? But still, for our understanding, the way we have designed these lectures are RNA viruses and DNA viruses. So we'll stick for it for now. But as we move, because of advancement of the studies, the fact is new studies are coming up. They can have both. Now, let's talk about their structure. And they have a very specific morphology. One of the things that I said, bad news, when I say bad news, so think of that in terms, and I also gave you the email. So that email, if you look at the email sign and logo, it's like an envelope there. So keep that in mind. When we talk of viruses, we talk of envelopes, and we're going to spend some time on that. The other important thing is that they divide, but their division is not like bacterial division, the mother-daughter. Mother, two daughters, mother, two daughters. We call it binary fission biology, basic biology. So they are not like that. There's no binary fission. But the term that we use is that all those parts are made separately and assembled. So that's what it is. It's more of like, I would say, analogies used like computer, for example, right? And then you took up like car manufacturing. So that kind of a thing you have to keep in mind, okay? Now, each and every property, as I said earlier, will have consequence. That's what we want to know. So if you know for sure what the nature of the beast is, then we can also qualify some of the statements that we used to have in the past. For example, philosophically, viruses are not living on their own. That's what it means. They are living as far as we are concerned because they cause problems. And then, of course, they are infectious. I gave you an example that, they have the ability to sustain the ecosystem that we have. And then again, they go and take over. It's like invasion in terms of taking over your protein manufacturing system. That's what they do. So in that process, if your cells are making proteins for their own good, it's just like somebody kind of invades in your home and eats up everything. There's nothing left in the refrigerator, freezer, so on and so forth. So that's what they normally do. So in order for them to replicate, they will cause damage, morbidity, and killing of this cell. And also keep in mind that our cells would not like it. So for them, it's an invasion, but viruses bring most of the time either take over your tools. It's like a guest come to your home and going to use your kitchen, your stove, whatever, microwave. But some of them, like, they will bring their own. They're not even dependent on you, right? So viruses may have this ability to come up with some of the codes on their own, and they have an ability because our immune system is such that the viral components must self-assemble. So that's an important thing, okay? Okay, just for a housekeeping thing, and I keep on saying that many of you do some activities in front of me that gets noticed. I don't even pay attention. And I used to pick on people on asking questions. So attendance is not mandatory. So instead of you looking at your cards or looking at many other things, at least, I usually say if you want to be in the first two rows, make sure that you give me attention because attendance is not mandatory. It gets noticed, right? Sometimes I say, sometimes I don't say. but please make sure that you give me that kind of respect, and that also encourages me to teach with my full vigor, and participation is important. But if I find out, well, you're just there in front of me like stooges, and you're not paying attention to me, and I can notice that, that doesn't good. But if you really want to play a movie or you're not interested, I don't complain. I think the best 2 benches are good enough. So all you need to do is once in a while, just say that and, make me feel that, you're part of it. But just, anyway. Now, when we talk of classification, we talk of structure. Again, I'm going to talk of size, I'm going to talk of morphology, and I'm going to talk of nucleic acid. And many terms I want you to keep in mind is they are self-explanatory. Like, for example, if I say a virus name is picorna virus, so it may look silly to you, picorna, but if you break this apart, pico means small, and there's RNA written over there. So if I ask you, hey, is picorna virus a RNA virus or DNA virus? It is a RNA because the name is hidden. You see that? Some of the viruses are toga virus. Toga in, I think, Italian, probably, if I'm right, or Roman, this covering of clothes are called toga. So you put on the dressings called toga. So this virus comes with this very special dressing. So there is a clue there. There is a message there. I want you to pay attention to that, okay? We'll also talk about there are many ways of classification. They're all there to help you, okay? And many a time is so simple. For example, if I say virus causing encephalitis, so probably is a virus that's going in the brain. If I say hepatitis virus, this virus is affecting liver. Plain and simple. So this is kind of, we call taxonomy that we normally use to help you and help ourselves to understand. Okay. Now, sometimes there's another hidden messages over here. Sometimes we use a term which suggests means of transmission of viruses. In this case, if I say arbovirus, so arbo basically means insect. So this means some of the viruses, they have something to do with insects. Okay. Sometimes we use the word in terms of host cell, as I gave you an example for hepatitis. So this means this cell, this virus has an affinity, likeness to go and reside in liver. Encephalitis in the brain. And sometimes we use mouse, human, plant, and bacteria. So that kind of gives you an idea as to where the virus wants to survive. If you get infected by viruses, what problem may you get? Sometimes we use the viruses in terms of their affinity, in terms of their liking. Regardless of whatever route they enter into your body, they have this we call tissue tropism. They're going to go and lodge over there. For example, if I say adenovirus, so adeno is basically a tissue that produces secretions, for example, glandular tissue, right? Adenoviruses, something to do with nose, something to do with upper respiratory tract. Adenovirus, the name suggests. If I say enteroviruses, of course, means intestine. So some of the viruses are very specific in terms of which and what tissue are they going to attach. Now, as I said earlier, a very important picture, and it will give you an idea when you want to assemble the virus together. Now, viruses can be enveloped or non-enveloped, right? And sometimes we call them as a naked capsid. So I'm going to explain that to you in the next few slides. I already told you for simplicity that the virus will either have a DNA or RNA. That's what the design of the viruses is. We separate them to DNA viruses and RNA viruses. So DNA, RNA adds to a structural protein. You can see from here, right? And then some of the enzyme and nucleic acids can be on top of that, like nucleoproteins, okay? And the whole structure, including genome, structural protein, and enzymes, such as nucleic acids, form nucleocapsid. They form a nucleocapsid, right? And this nucleocapsid, if it doesn't have, it's just like you write a letter. I used to give example like a postcard. I'm going to give example again, or an old style letter that has to be put in an envelope. So if there is no envelope, we call it naked capsid virus. On the other hand, same thing, if you wrap it up into an envelope, right? And this envelope will have a glycoprotein membrane. Okay, we call it enveloped virus. So you can see the two major classification in terms of enveloped virus. But if you look on the top, these are, for example, you can see some of the components of naked virus. The only difference that it will have protein, it will have lipid protein and glycoprotein, and these are the properties based upon their structure. For example, you can see that the one which has a naked capsid is stable in dry and acidic environment. Okay, the one that has membrane, because the glycoprotein membrane is going to get digested in acid environment. So this will be the basis of your understanding in terms of whether a virus has a capsule or it doesn't have a capsule, and what are the implications for that. Okay. Now, as I said earlier, your book divides that into the major concepts. These are again memorizing slides. I'm sorry if it's a little small on that, but those of you who get iPad or whatever can expand it up on your own machines. Again, the whole idea is that we divide them into envelope or naked. These are the terms that we normally use. And we also divide them into DNA and RNA. So if you pay attention to the top one, and you will see the top one basically is a DNA virus, and both of them may or may not have a capsule. So if you look at DNA viruses are either enveloped or naked. And in enveloped viruses, we have three important viruses, and all of this information you need to know. Okay, so in enveloped, we have pox virus, we have herpes virus, which we have HepDNA virus, HepDNA. But again, as you break it apart, you say Hep means liver is a DNA virus. It's there written over here. As compared to naked capsid, we have polyoma, papilloma, adeno, and then we have parvovirus. Now, in parvo, within the bracket, it say SS. That's what I said, that you have to know a little bit of genetics. We don't teach you, but it's going to be very 1+ for you to know genetics, because genetics is going to come over again. So SS stand for single-stranded DNA, whereas DS stand for double-stranded DNA. So you have to understand this terminology, which is over there. Now, if you go and look at like RNA viruses, and then again, RNA viruses, we divide into a plus strand of RNA or a negative strand of RNA, okay, or both. Right? And sometimes we develop an RNA strand from DNA. That's like very basic genetics in terms of the way RNA works and way DNA works. So you have to know those major differences. Now, in these different classification, we again have naked and enveloped, and there are a list of viruses there that you need to remember, and we will basically discuss all of them as we move along. So it's just like a first general lecture. The most important thing that you can see, for example, in the last one over here, it says it is a plus RNA virus, which RNA will come from DNA. Right? That's why, remember, I didn't want to confuse you with both RNA and DNA. But the most important thing is an enveloped virus. It is a retrovirus. It's an HIV virus. So you can imagine that there's going to be a challenge for us once we move and discuss that in terms of AIDS. There are tons of mnemonics, and you can help yourself. And one of the things is that when we talk of viruses, size matters. Okay, when we talk of viruses, size matters. And I just picked up this slide from the Guinness Book of World Record of the smallest child. Holds a record for the smallest child. It happens to be somewhere in India, I believe. But the important thing is the size of virus is determined whether it's going to cross a membrane or not. So you need to know the size of viruses. You need to size of respiratory membrane or all those membrane gaps and this and that, and see if this virus can penetrate or not. That will actually give you an idea how and why we do that. Okay? And when we go into, there are a lot of different, as I said, figures in your book. And I would also encourage you to draw your own. All these slides are just for your conception that we can divide this into human DNA viruses on the left, human RNA viruses on the right. I want you to pay attention to how they replicate their genome. So you can see from here, these two arrows point how they replicate their genome. And you wonder, why do we need to know that? We need to know that because we want to treat it. Okay, and the other important thing I would do is that make sure that you know the size of viruses as compared to bacteria. So this is a bacterial size which is roughly 6 micrometer long, Escherichia coli. So you compare that, and also keep in mind when I gave you an example of a bacteriophage, a virus that infects the bacteria. So of course it has to be smaller and inject the RNA within this when we talk the genetic transfer of resistance. The most important viruses are human DNA. You can see if I ask you, these are the questions I normally ask. What is the smallest human DNA virus? So of course, they're all listed in terms of their sizes. So parvovirus is the smallest, which is picorna, as the name suggests, is over here. Then we have larger viruses. Right? Why do we know the size? One of the reasons we know the size is they're going to penetrate into cells. And many times they want to go into cytoplasm and the nucleus. If the size is too big, like for example, pox virus is a big virus. It's not going to go and penetrate into the nucleus. Okay? In the same size, remember chlamydia. This is not a virus. We talked that as a bacteriology, but we talked about the size of it. Remember when I talked, size in terms of even bacteria, in terms of infection they get. The other important thing that you have to keep in mind is that most of the human DNA viruses do not have lipoproteins. Do not have lipoproteins. And the other important thing from this slide and is about the structure, whether they are cylindrical or they are spherical or icosahedral. So they are very well arranged. So they can be, all this kind of very properly arranged in terms of assembly that we normally see in these cases. Okay. The other point, if you remember, I made was that retroviruses are special. And these retroviruses are the one that cause AIDS, right? They are special. I want to emphasize that. I'm going to talk about that in the basic structure and give you a detail afterwards, that how do they synthesize messenger RNA? And if you go back to previous slide, everything is going to be supplement to the next slide. So how are they going to synthesize RNA? So they have an ability, okay, let me put it back that way, a little bit of biochemistry. In order for you, and genetics as well, in order for you to synthesize messenger RNA, you need an enzyme which is called reverse transcriptase. It's called RT. Right? Now, what happens is that this particular virus, especially AIDS virus, brings its own viral RT. Right? So it brings its own viral RT to form DNA, and then use cell DNA-dependent RNA polymerase. So what happens is that it kind of is weird. So it has to make an RNA before it's going to make a DNA. So what it would do is that it's going to have that enzyme to form first, and then use your cells which help it to expand upon division in terms of DNA-dependent RNA polymerase, which is another enzyme to synthesize that. So that basically, if you understand a little bit of genetics, that is the problem, and that is the question: why and how HIV causes disease, right? So you may have to spend, I don't know, half an hour and an hour try to dissect it, understand it, but it needs a little bit of prior knowledge of genetics. It needs a prior knowledge of how messenger RNA is made. What is messenger RNA? What is the difference between DNA and RNA? What is the problem here? What is the problem in HIV before we treat it? Okay, so that's important in this case. Now, a little bit of reverse transcriptase. So sometime, I just give an example. This is how we ask the question. Reverse transcriptase RT is important. So I would say, which DNA virus uses a reverse transcriptase to its genome, right? And I already told you HIV. The other important, what you call a virus that does so is human hepatitis B virus. So it's a hepatitis B virus, HBV. And again, you know, the both are important and both have a big bearing on what we do. Now, let's go back and look at the structure element. I already told you, we talked about capsid, we talked about envelope, we talked about genome. And if we were to look at the picture over here and the difference between a naked capsid versus a envelope, and I gave you an example as well. The other term that we use is when I say virus particle, what I mean is that this consists of nucleic acid genome, and it is packed into a protein or a membrane envelope. So that's the whole idea, and this is good enough to cause infection. Now, if you look at, for example, the structure of a naked capsid on the left-hand side with that kind of icosahedral thing, so you can see that it's very well built and organized. And within that nucleocapsid, we have an RNA. So we have an RNA over here, right? RNA over here. And all of this structure then is protective and put it in an envelope. And then envelope, again, is very well organized, right? It has that in the center, a nucleus, a naked capsid over here in the center, and is very well protected. So it's very well protected. The other important thing that you can see from here, like the most important thing, like human cell, the outermost covering of an enveloped virus is the same that we have on our cells, which is lipid bilayer. The lipid, and I'm gonna come back to teach you where would viruses get it from, okay? Then they are studied with, like our cell membrane, studied with different kind of, proteins, lipoproteins, glycoproteins. Each of one have a purpose. So these are called structural proteins. Some of them are structural protein because they are part of this membrane, and some of them are glycoprotein. Can anybody tell me what is the significance of a glycoprotein? We talked about glycoproteins in bacteria as well. Say it again. Louder. Very good. Adhesion. Very good. Adhesion. The word glyco means adhesion. This is the most important thing that you have to understand in terms of viruses. They need to adhere. Very good. Now, also keep in mind the structure of the viruses may be different as we go along. But if you have all these things in your mind, and when I talk of pathogenesis, you will kind of appreciate as to where I'm coming from. Now, a little bit more on what I just said for you to learn as mnemonic. Again, I give an example of a postcard versus a letter. And then I gave an example for the letter is that this is sticky. You just have to kind of stick those stamps over there, this little bit of liquid. So that's where the glycoproteins are coming from to attach. So the analogy is that the glycoprotein sticky stamps. That's what we're trying to push upon you. So the other most important thing is that all fecal oral viruses, do not have a glycoprotein outermost layer. And what could be the reason? I'm just going to make you participate in what do you think could be the reason? Yeah. Yeah, what exactly is happening? I mean, where and how? When you say fecal oral. Sorry? The rule stands. The answer is here. Acid, heat, and detergents. So this means for fecal oral viruses, you have to swallow them and they're going to go into your stomach. And if they have outer glycoprotein, acid is going to chew that up. So they, for their survival, better not to have it. That makes sense? Right? And where would be the detergent present in a human body? Physiology. Louder. Yeah. You said something. Don't be shy. Stomach has acid. There's no detergent in the stomach. Which part of intestine? Duodenum. Very good. Duodenum. Because we want lipid emulsification. That's the action of bile. Bile is a detergent. You have to break apart, because if you know the soap, what makes soaps as antiseptic, that's again written in detail in chapter 3 that we have lab about. So what makes soap very effective? One is a detergent action, which is to break apart the larger lipid molecules, and lipid molecules from the outermost layer of the bacteria. Good. Okay, and then heat naturally, because our bodies are heated. Inside, there's a body temperatures. Good. Now, a lot of the tables are there in your book. For example, in definition, what is a viral capsid, which is a protein coat surrounded by the genomic material, right? And you have a repeating. If you look at those structure elements, they are repeated units because they are very well organized. So these kind of capsid, we call them like capsomere. It's like what you call, you make that scaffolding there, or building blocks. So these building blocks are identical protein subunits, like a structural element over there in these particular viral capsids. Now, each and every structure has a function. What's the function of viral capsids? They promote viral assembly. They protect the genetic material which is inside, facilitate viral attachment to the cell, attachment and field with the host cell membrane. That's because of the glycoprotein that we discussed earlier. And then when it attaches over there, it can deliver the genome to wherever it wants to do that. Okay. Now, if you look at the virion structure, like a naked capsule, component is protein, and these are the properties, right? These are the properties of the naked capsid, right? Don't confuse that with the envelope, because one of the reasons is that the outermost protective protein capsule is that it is stable to temperature, acid, proteases, detergent, and drying. So what it suggests to you that viruses on the table or fomites can stay for extended period of time because they can resist drying. So they don't need to multiply. They can just sit over there. They don't need to multiply. They cause infections. And the other important thing is that I want you to keep in mind, we teach you something to give you the basis for that. We don't teach you advanced virology. We don't teach you advanced immunology. We don't want to confuse you. But you as a student should know that exceptions do exist. As I gave an example, that some of the viruses may have both RNA and DNA. Okay? So keep in mind, whatever we teach you, because I know some of you do a lot of reading and some of you are ahead of me as well. So there are exceptions over there. We don't teach you. We don't, well, unless you want to, there will be at the most 1 or 2 questions which is going to be of that hard level that's going to test you whether you have had an opportunity to go beyond whatever textbook. But keep in mind the exceptions do exist. Now, if you term of the virion structure, the way it is designed is it can spread very easily. It can dry out, still retain infectivity, can survive the adverse condition of the gut. I just told you that's why we don't have the membrane. And then again, also keep in mind that whatever detergent, one of the questions I asked was, which of the following are antiviral? So keep in mind, soaps are not antiviral. Okay, so even if you wash your hands, keep in mind that the viruses can resist detergent. Or the other important thing that when we talk of these viruses, if your body is making antibody to that, it may not be sufficient enough to give you immunoprotection. So these are the things that we normally keep in mind. And then when I use the term virion, what I mean is the complete virus particle. Okay, so it can, for non-enveloped, it can be nucleocapsid. For envelope, it has to be nucleocapsid plus the envelope, depending upon which virus are we talking about. Okay, so let's take, for example, the structure of a envelope virus, which has a membrane, lipid, protein, glycoproteins. These are the structural elements over there. And those of you who are more visual, I think these next few slides are just kind of a legends of what I've already given in that figure. So you want to put this figure in front of you and go from there. And again, you can see that the property of those viruses is that if those viruses, for example, happen to have envelope, they are labile to environment. So they can kind of go, because simple biochemistry, if you have an outer lipid membrane, you need a little bit of moisture there. You need, it's going to change with heat. And if it's dry, then again, everything will be changed. So these are some things that may modify the cell membrane. And then again, will make that virus unfit for causing infection. Okay, so those viruses, which are enveloped, what they need to do is that they need to stay wet. They have to have a moisture there, right? And I already told you they cannot survive into gastrointestinal tract because acid is going to chew them up. They spread by large droplets, sneezing, coughing, right? They are in secretions and then in the blood. The other important thing to keep in mind is that when the viruses infect the cell, there are 2 things that can happen. One thing is they are released from the cell, with the cell being intact. The other thing is they can kill the cell, right, and then be released. So in this case, these particular viruses do not need to kill the cell to spread. They can bud out. They can be released, right? And then again, as I said earlier, they need a robust immune response for antibody and cell-mediated. They can also elicit hypersensitivity and inflammation to aggravate the immunopathogenesis that you may see in this structure. And the most important thing, as we talked of bacteria, is that the challenge for therapy is that how can we stop viruses replicating? That's the basis of the therapy. Okay, so if you understand the next couple of slides, it will be very easy for you to understand, consult the patient, and give your opinion on that. Now, keep in mind, when we talk of viral replication, we divide that into 2 phases, early phase and late phase. The early phase has 4 steps, and late phase again has 4 steps. The very important thing, once the virus wants to go, it is going to recognize the target cell. So viruses are very target specific. right? So it's going to go, there's a mechanism over here, it's going to go after one particular cell. Could be any part of the cell. Then the second step is going to go and attach to it, right? The third step is going to penetrate that. And the fourth step is that it has this protein coat, it's going to take this protein off and then inject RNA or DNA virus into it. Now, if you keep this in mind, this is called pathogenesis. So whatever viruses do, we need to undo that. So this would suggest that we have 4 different types of drugs that are going to stop the early phase. They're all based upon pathogenesis. Okay, too late. It's already within the cell. Now what we need to do, because the moment it gets into the cell, it's going to start macromolecular synthesis. It's going to assemble proteins, lipid, this and that. It's going to take over your structure, molecule structures to make all this energy level. It's going to make all those parts in different parts of the cell, assemble them together, and release them out of the cell. Right? Now, that's another challenge for us. If we fail to come up with a therapy that's going to stop the first 4 steps, we're not going to give up. So we're going to go and stop macromolecular synthesis. We're going to go and stop assembly of viruses. And we stop the budding of the viruses and stop the release of viruses. So these are all important, but also keep in mind that stages 2 and 3 basically rely on viral capsid. That depends upon what kind of virus that is. So keep that in mind, okay? The early phase and the, okay. So this is now a slide that is going to appear in each and every virus that I'm going to talk about from now onwards. But in today's lecture, I'm just going to give you an overview. And it also keep in mind that it's going to give you an overview of how we are going to deal with viruses and what are the antiviruses available and how and what's going on. So let's take step by step. For example, if you go back to the previous slide, I said the virus over here is going to come, number 1 step, recognize. So there's an ability in the viruses to recognize where it's going to go. So what do you think the virus would have to recognize a particular cell? Sorry? Receptors, not MSC, receptors. Because remember, for any recognition, these are receptors. The virus is designed for that. It's going to be, and it's going looking for a corresponding receptor. So that is the very first step in terms of recognition, where viruses will look for this particular, and then once they find that, the second step is attachment. Right? They're going to go and attach. So the first line of defense of antiviral therapy that we have developed consists of antibody receptor antagonists. So we will have antibody receptor antagonists to stop these 2 steps. Simple. Okay, we failed. The virus gets into the cell. It goes, you can see from here, it picks up the outer membrane, goes into the cell. It penetrates. It penetrates the cell. So it penetrates the cell, and we couldn't do anything. As of now, we have nothing to do in terms of penetration, but we know that once it penetrates, it's going to take these coats off and start sending a messenger RNA or DNA to replicate. And this step, number 4, we call uncoating. Okay? So virus uncoats, takes the coat off. Simple as that. So we have, and I want you to remember that, some of the, in this lecture especially, because virology, we're going to teach you antiviral drugs as well, so you have to remember the name of the drugs. So the 4 important drugs which are in the market for antiviruses are, you can see from there, amantadine, eryldone, rimantadine, and trometadine. So you can see most of the A genes are there. And if you look they come with different names. So these, if they ask you what is the mechanism of action of amantadine, for example, Commons drug, you know that it's there to stop uncoating, and it's there in your memory. What does uncoating mean? Okay. Now the next step is that, let's say you fail. Now the genome is going to transcribe the virus for protein synthesis. So there's a next step over here. Number 5 is transcription. Okay, so we have some of the drugs which are going to attack transcription, and these are interferons, antisense oligomers. We'll discuss in detail, but they are there to stop that. Okay, we fail. And now the viruses have started making protein synthesis. They're making protein synthesis. We can still go for interferon. So you can see the robust activity of interferon, which is still a bit non-specific. It's there, right? So we are going to go for number 6. And then we can also go and stop that macromolecular synthesis over here in terms of replication of that particular genome. Because that genome, you can stop transcription, you can stop replication of that genome in the viruses. And then we have nucleotide analogs and phosphonoformate. These are the drugs that we have. And some of that will be overlapping for anti-cancer therapy as well. That's pretty much the same. Okay? Number 7. And number 8 is that these viruses are going to assemble all these different components put together to be sent out. So what we do is, because many of them are proteins, so we develop protease inhibitors to stop the assembly. So we develop protease inhibitors. That's also very important, especially for HIV. If you, I'll teach you when I teach you HIV that there are cocktail of protease inhibitors that we normally use for anti-HIV therapy. Okay, and then finally, viruses are made, right? But these viruses to lyse the cell and be released. Okay, so we can even stop that happening. Okay, we may not be able to do that. But the other important thing is that the difference between a naked virus and an envelope virus is, this is the system for naked virus. It's naked. It doesn't have the envelope. Now, the question is where it's going to pick up the envelope. So you can see that envelope is going to be picked up by taking a chunk of the cellular lipid barrier. Okay, so it takes this cellular lipid barrier of your own cell, wrap it around the virus genome, right? And then we call this concept bud out. So these viruses are bud out and released. Okay, so we can also have drugs which are discussed later in terms of stopping bud out and release of the viruses. Okay, so these are the major kind of replication things that we normally keep in mind. And then again, also keep in mind that the rest of the slides over here are, if you know this concept, you know that if the virus, we're going to start with the first step with the anti-receptors. We have to find out what is the receptor we need to stop on the virus or on the cell. So we can develop drugs particularly. So because we know some of the viruses for HIV, we know the viruses for different cells. And just to give you an idea, that if this is a virus like HIV, the target cell is T cell, receptor is CD4. This Epstein-Barr virus, the target cell is B cell, complement receptor. Rabies, so you can see from here in the general slide that they are very specific host cell receptors, and they are very specific things that are there. Okay, and I'm going to leave on you to go on your own and read out some of the legends that I already explained to you while I was explaining to you those basic replication. So this slide that I'm using over here in terms of replication is pretty much the same. So you can go back and look at what is happening in macromolecular synthesis, which is just a recap of basic genetics. And many a time we ask these questions, that what is the difference that one virus is more infectious than the other. So that again will give you an idea that some of the viruses that they bring their own enzyme to help the virus to synthesize the components are more dangerous, because the thing is, because these viruses, their genome can synthesize all the required properties directly with host enzymes. These are some of the things that we keep in mind in terms of what's happening. And lastly, I'll give you this as an assignment as well. This is a very good slide for those of you who want to recap basic genetics. This is a basic genetics slide. And if you understand that, right, I mean, I cannot teach you genetics in this lecture, but you can see from here what is single-stranded DNA, what is double-stranded DNA, what exactly are the different molecules, and how the assembly takes place in terms of the genome. So if I ask you what is a single or double-stranded or linear or structural, so all these genomes of different viruses have a structure element. And these structure elements will be broken up by the drugs that we have. So if I teach you this particular drug is going to go and act on the segmental genome, so you know where is the segmental genome. So you have that idea that what exactly I was talking about, and especially for this case, this segmental genome is important because retroviruses have it. So if you don't understand the basic genetics, what is the segmental genome, you would not be able to understand what are the problems that we have in terms of treatment, in terms of the therapy that we normally use. Okay? And then growth cycles pretty much the same. And one or two slides, as I said earlier, that will just help you to give an idea of what normally viruses are. And some of the things are going to be repetitive. As we move along,